All right, so this video is going to be all about molecular structure again, and we're going to talk about lesson number 8, types of chemical bonds. So we're going to primarily talk about ionic and covalent bonds. That's our first thing. So ionic bonds are going to be between a metal and a nonmetal. This should be review for you. So something that's a cation bonded to something that is an anion. Or we say that's a positive ion bonded to a negative ion. The cation is going to lose electrons, so these are going to be elements, generally metals, that are happy losing electrons. They're going to lose their outer valence shell on that Bohr model so that they look like the noble gas of the row before, and I'll show you that here in just a second. Whereas the anion, the nonmetal, wants to gain electrons. So where their location is at on the periodic table, they really, really, really need to gain electrons. So I'm going to show you just a real quick periodic table that I have labeled. So these metals, anything in column 1, column 2, any of these transition metals, and these metals in column 3, these guys really are okay losing electrons, because when you look at how many valence electrons they want to have, everything wants to get to 8. Well, they have fewer than 3. So it's easier for them to lose those valence electrons and look like the noble gas of the row before than it is for them to gain all those electrons. So for these nonmetals right in here, because remember this is our dividing line for metals and nonmetals, but these nonmetals right in here, they form 3 minus, 2 minus, and 1 minus ions. It's really easy for them to gain. Like everything here is just one away from being full on the Bohr model. So that's what it shows you in the lesson. So let me just take you through this example really quick. So we have a sodium atom, and remember from previous units that sodium is in the third row. So that is why it has one electron in that 1s orbital, but it has one electron in its outermost energy shell in the Bohr model, and that's what this electron is right here. So it just has one. Whereas chlorine has 1, 2, 3, 4, 5, 6, 7 in its outermost shell. So it is one short, and sodium's got one too many. So what sodium does, it's really easy for sodium to form this sodium ion. It literally is going to transfer an electron to chlorine. Chlorine is like, I will take that off your hands, and sodium is more than happy to get rid of it. And now you see that entire third energy level disappears, and the sodium is still sodium, but it looks like neon of the row before. So it still has 11 protons, but now it has 10 electrons, which is why it forms a 1 plus ion. And the chlorine, it's still chlorine because it has 17 protons, but it has gained 1 electron. So it now has 18 electrons, and it's now full on its outer shell. And this positive and negative attraction is what we call an ionic bond. So this would form the ionic compound of sodium chloride. You can use this for any compound, any ionic compound. So another thing that we kind of need to talk about in this unit is something called electronegativity. And it's when something forms a compound. So that's the key here. You have to form a compound. Noble gases don't react, so we generally don't include them in electronegativity values. But when they're reacting, it's how strong you are, or how much you want to pull those electrons closer to you. So if you guys remember, these guys over here really, really, really want electrons. So they're going to be really electronegative, meaning when they form a bond with something, they're either going to flat out take the electron, or they are not going to share evenly. So nonmetals tend to have very high electronegativities, whereas metals have very low electronegativities. So here's kind of the trend on the periodic table. As you go across a period, electronegativity goes up. So the things over here have a higher electronegativity than the stuff over here, which makes sense. These nonmetals right here have a higher electronegativity than these metals over here. And then as you go down, your electronegativity values tend to decrease. So even over here, as you go down, they tend to decrease. And that's just because the atom gets bigger as you go down. And they're just not as strong. Like fluorine is a pretty small atom, and it's pretty strong in terms of its electronegativity. It's actually the most electronegative element and francium down here would be the weakest electronegative element. So that's kind of the electronegativity trends, and you'll need to know electronegativity when you start talking about covalent bonds. So that's our next one. So what is a covalent bond? It's where you have non-metals joining together. So we have a non-metal bonding to a non-metal. You literally have something that wants to gain bonded to something else that wants to gain. So you're not going to be losing or gaining here. You are not going to have charges here. They are strictly going to share electrons. And there are some examples given to you, like here, where you can show them overlapping. So this would be like hydrogen, one proton and one proton, but they're going to share this electron pair between the two of them. This would be oxygen. And oxygen is going to share these two pairs of electrons. This is what we would call a double bond. So this would be oxygen double bonded to oxygen. This one would be a single bond because they're only sharing one pair of electrons. Nitrogen is something that shares three pairs of electrons, so you would draw it as a triple bond. The main thing to know about covalent compounds is, yes, they share. They don't always share evenly. And that's where you'll get the term polar covalent from. You might have heard that before in biology, talking about how water is polar. That's because hydrogen and oxygen are bonded together. And in that bond, oxygen and hydrogen are sharing a pair of electrons, but the oxygen is a little stronger, so it pulls it closer to itself, making it slightly negative, whereas the hydrogen is now slightly positive. So they're sharing, but they're not sharing evenly. So just a little bit on where you might have heard of covalent bonds or polar covalent bonds. So we can have polar and they can be non-polar, depending upon how they share, evenly or unevenly. You do need to be aware of these diatomic molecules. There are 7 of them, and ironically enough, they form a structure that looks like a 7 on your periodic table, pointing to hydrogen. So these 7 are nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And they form a 7. And they point to the last one of hydrogen. Why are these guys so important? They are pretty unstable. They're pretty unhappy, meaning that when they are existing in nature, they only exist in pairs. So you are not going to find them by themselves. So instead of nitrogen being by itself, atmospheric nitrogen is N2. Fluorine would be F2. Hydrogen would be H2. Oxygen would be O2. That's why we've always written oxygen as O2, because that's how it exists in nature. The next part of this lesson is talking about naming and writing formulas for covalent compounds, and only for covalent compounds. So we're going to use the prefixes. So this should be a little bit of review for you. There are some basic rules. We use no prefix, mono. So no prefix mono on the first element. You use all the other prefixes. You just don't use mono for one. The second element is where you put the IDE at the end, and you will always have a prefix on the second element. It doesn't matter what the prefix is. So there's a list of prefixes that it gives you in your notes, what to use, but mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Basically, you just look at the formula. You go, okay, how many sulfurs do I have? I have 1 sulfur. Well, I don't use mono on the first one, so I just leave it as sulfur. And then how many oxygens do I have? I have 2. Well, the prefix for 2 is di, so it becomes dioxide. If I have the compound of disulfur dichloride, how many sulfurs do I have? I have 2 of them. How many chlorines do I have? I have 2 of them. So S2Cl2. And you literally just write it in the order that it gives you. So these are probably the easiest to name. The next thing that this lesson takes you through is a little bit on what a polyatomic ion is. And for our purposes, you guys just need to know that there are more than one element that's bonded together, but it's still an unbalance of charges. So they're still going to have a charge to them. You will treat them as a single unit. So don't separate them out. Just treat it as one thing. So if you're given like What happens when sodium and nitrate join together? Well, I look on the chart that it gives me. So I know sodium from the periodic table is in the first column. So I know sodium's charge is always a 1 plus. And then if I look on the table that it gives me right here, you don't have to memorize them. It tells me that I have nitrate, which is also a 1 plus. So NO3 with a 1 minus. So I have sodium 1 plus bonded to nitrate that is a 1 minus. And when I put those together, if I use the least common multiple method, I put them together. 1 plus and 1 minus would cancel each other out, and that's what I want in a compound. So it's NaNO3. What if I had magnesium and phosphate bonded to each other? Well, magnesium has a charge of 2 plus because it's in the second column on the periodic table. Phosphate is PO4 with a 3 minus charge. Remember, I need my charges to balance out. I need my charges to cancel. So I'm going to use the least common multiple method, which is what LCM means off to the side. And I need to get these to their least common multiple, which is 6. So how many magnesiums do I need to get to 6 positive? I need 3 of them. How many phosphates do I need to get to 6 negative? I need 2 of those. So that's why the formula becomes Mg3 and then PO4 too. And you notice I put PO4 in parentheses to show that I need 2 of that whole group. So now I have 6 negatives and 6 positives. Down here in this example, I have ammonium and I have phosphate. So ammonium is NH4 with a 1 plus. Phosphate is PO4 again with a 3 minus charge. I need to make the charges balance. So right now I have 3 negatives and I have 1 positive. So I need more positives. So I multiply this one by 3, and now I have 3 positives and 3 negatives. So I just put it together, but I need 3 of that group. The nice thing is about the naming, you just name them as they are on the chart. Most of them end in ite or ate, so they're not ide. Elements are ide, IDE. The only one that's really ide on the chart is hydroxide. The rest of them are all eights or ites. So if I have this example down here of KMNO4, MnO4 is the polyatomic ion if I look on the chart, and it's bonded to potassium. So I just put it together, potassium permanganate, which is what MnO4 is called. When it becomes kind of tricky, remember when we were naming ionic compounds, if something is in column 1, column 2, or column 3, you're good, which potassium is in column 1. I don't have to do anything fancy with it. But if it is a metal that's a transition metal in this group down in here, the inner transition metals, the transition metals, or even this group right under the staircase, right here under the staircase that are metals, I have to use the stock system with them. So I'm going to give you an example with that. I have cobalt bonded to hydroxide. Well, what you want to do is just name this cobalt hydroxide. But cobalt is not in column 1, 2, or 3. So because we don't know the charge, I can't just assume that I know what it is. I have to figure out what the charge is. So you must use what we call the stock system. Remember, we must use a Roman numeral to mean the charge. So if I have cobalt and hydroxide bonded to each other, I don't know the charge of the metal, but I do know the charge of the non-metal. So hydroxide is a 1 minus charge, and I have 3 of them. So that makes it a 3 minus. So that means the cobalt has to be a 3 plus. And therefore the name would be cobalt 3 hydroxide, because that is the charge of the cobalt. And you would be incorrect if you just called it cobalt hydroxide. So hopefully this helps navigate this lesson, and let me know if you need any more assistance.